So here we're going to talk about section 7.4 of your book, which is going to talk about double angle identities. We are going to start by going through really how you get these identities and then giving you the identities in all their forms. So the first thing I'm going to talk about is how we derived them, which we derived them using our sum identities that we talked about last time. And so I'm going to talk you through this. If you want to just give it a try like it's a warm-up, you are more than welcome to do that. Just feel free to pause the video. So if I want to use my sine sum identity, first off, this is my alpha, this is my beta in theory, but they're both just thetas. I'm going to plug into that identity from last time that tells me to do sine of alpha, or in this case theta, times cosine of beta, which is also theta, plus, since I use the same sign, and then cosine of theta, or your alpha, and sine of your beta, which here is alpha. When we're looking at these are really like terms because multiplication, your order doesn't matter. So I can combine them together and it would just be 2 sine theta cosine theta. And what you're going to learn in a second, sine of theta plus theta is really sine of 2 theta because plus 1 is 2. So this is actually going to be your first identity. To derive the second one, we're going to do our cosine. So with cosine, you start by doing cosine of alpha, in this case theta, times cosine of beta, or also theta. It's the opposite sign, so this is going to be minus instead of plus. And then sine of each of them, so sine of theta, sine of theta. Doing this multiplication, this is really cosine squared of theta minus sine squared of theta. And again, if we add these together, that's really 2 theta, so your second identity is that cosine of 2 theta is cosine squared minus sine squared. Lastly, we're going to use our tangent identity the same way. Again, this is my alpha and my beta. So when I do this, it's going to be tangent of theta plus, because the top sign matches, tangent of theta, because it's tangent of alpha plus tangent of beta, all over 1 minus, and then here I multiply them. So tangent of theta times tangent of theta. If I do some of this condensing, this becomes 2 tangent of theta on top. On bottom, it's 1 minus tangent squared of theta. And again, theta plus theta is tangent of 2 theta, so your third identity is this one right here. Okay, I show you this that you have the ability to derive it should you ever need it, and you know really where these came from because it didn't just come out of nowhere. What I have here is all the different variations because there are more than one way you can use each of them. You'll notice on sine, this is exactly the one we derived a minute ago. And then on cosine, the first one is, but I'm going to show you how we've derived these second two. If I wanted to get to this second one here, what they did is they used their Pythagorean, and in your Pythagorean, remember that you know sine squared of theta plus cosine squared of theta equals 1. And they replaced sine squared of theta with what they know it equals, because we know that sine squared of theta equals 1 minus cosine squared of theta if you manipulate that identity. And then when I plug this in, you know that cosine of 2 theta is equal to cosine squared of theta minus 1 minus cosine squared of theta. This negative does have to distribute to both of these things right here. And so it's going to be cosine squared minus a negative cosine squared gives me 2 cosine squared. And then minus 1, which is exactly what we have right there. Okay, this third one, they did the exact same thing, but instead they replaced cosine squared with what it equals. So they replaced cosine squared with 1 minus sine squared and manipulated it. So again, the one you have to know is this top one. You are welcome to memorize these other two or at least be able to derive them. They can benefit you sometimes in proofs or in different problems, whatever it is. On tangent, the top one is what we derived a second ago. This bottom one, they used the quotient identity because your quotient identity does still apply, that you can use sine over cosine. It just now has to be sine of 2 theta over cosine of 2 theta. So again, like with sum and difference, this lets us find more angle values for exact values without a calculator. Here we are going to primarily focus on the type where I give you a ratio, and then you're going to be asked to find all of these different trig functions. So with these, this is like the last type that we did last time on 7.3. I always start by drawing my triangle. Here I only have one triangle because it's just my theta. Secant is the reciprocal of cosine. So the 5 is my hypotenuse and the 4 is my adjacent. And then you can do the Pythagorean theorem to find this missing side, which is 3. What I always suggest, if you look back at your identities, you're going to primarily want to know sine and cosine really throughout all of these of your regular theta. And so I'm going to go through and just label what's sine of theta, what's cosine of theta, and what's tangent of theta so that I can work from there. When I figure out these values, I am also going to think about the quadrant so that I can fill it in because I want to plug it in correctly. Your sign will matter. This is in quadrant 4. Because between 3 pi over 2 and 2 pi is quadrant 4. And so I know that sine will be negative and tangent will be negative, but cosine will be positive. If I go ahead and fill them in, sine is negative 3 over 5. Cosine is positive 4 over 5. And tangent is negative 3 over 4. And really then what this mostly wants you to do is go ahead and just plug these into the actual values, and I'm making, or the actual identities, so that you can find the value, and me making sure that you can correctly evaluate any of these. So for sine 2 theta, you do 2 times the sine of theta times the cosine of theta. We know sine of theta is negative 3 over 5. We know cosine of theta is positive 4 over 5. And then we need to do this multiplication. Do remember this 2 is technically over a 1, and that will allow you then to multiply straight across. So when we do this, 2 times 3 is negative 6, times positive 4 is negative 24. And then 1 times 5 gives me 25. So this would be the sine of whatever angle is twice as big as that one. So we don't necessarily know either angle measure, but we can calculate the sine of it. Going ahead and doing cosine. This one is going to be cosine squared of theta minus sine squared of theta. Cosine of theta, so it's 4/5, and then I'm going to square it, minus sine of theta, so negative 3 over 5 squared. You do want to start by actually squaring that, so 4/5 squared is 16 over 25. Minus negative 3/5, the negative will cancel, and it'll just be 9 over 25. And then we do 16 minus 9, and we get 7 over 25 for the cosine of whatever angle is twice as big as this one. Last but not least, you do have 2 options for your tangent one, just like we technically did with cosine. And what I want to point out, we currently already know sine and cosine, so doing our quotient is actually going to be the easier option. You can do this as well, but there's just a little more actual math embedded, and I already did the work of getting sine and cosine, so I might as well let that benefit me. So when we do this, sine is negative 24 over 25, cosine is 7 over 25, and then I'm going to multiply by my LCD, and you get negative 24 over 7. And that is done. So here we're just going to do 2 more for practice. One friendly reminder that as you move up in math, you're going to want to make sure that you can do these things without a calculator. So it is a very good idea to challenge yourself in that way as you work through these. With this, if you want to give it a try, go for it. If you would rather listen to me talk about it, that is also totally fine. Do what you're prepared for. When you're setting up your triangles, back in Unit 1 when we did this, we talked about how we didn't really label the negative on there. I'm just going to make this a root 3, and I'm going to make this a 7. And then I'm going to find that missing sign. Where I'll think about the signs is when I get over here to the quadrants. When I do Pythagorean theorem, 3 plus 49 gives me 52. So this is the square root of 52. You do always want to check if you can simplify it. 4 does go into this, so this is really 2 root 13. But you can leave it either way, and I'll kind of show you how it's going to work out as we go through. your final answer does need to be fully simplified, and so just be careful there. Okay, we already knew tangent, so I'm just going to pull this down. It is in quadrant 2, which means sine is positive and cosine is negative, so I'm going to go ahead and label that. Sine of theta is going to give me square root of 3 over, you can leave it as 2 root 13 or square root of 52 here. It's actually easiest to leave it as square root of 52, and I'm going to show you why as we work through this. And then cosine is going to be 7 over root 52. And this is where it really will pay off to not rationalize yet. And really, I'm going to show you here to not simplify yet. And it's really just how the math specifically works here, and finding you an easier way to do it without a calculator. So when we go to do this, sine of 2 theta is 2 times my sine of theta, which is root 3 over root 52, times my cosine of theta, which is negative 7 over root 52. Again, the 2 is over 1. When I multiply straight across, 2 times root 3 times negative 7 is negative 14 root 3. The reason I didn't necessarily recommend simplifying is really right here. I am about to multiply root 52 by root 52, which I know just cancels to give me 52. I am going to go ahead and simplify this. Both of those numbers are even, so I can divide a 2 out, which gives me a 26 on bottom and a 7 on top. And that's going to be my final answer. But if you notice, I didn't have to rationalize or simplify any radicals because they all just kind of canceled. Now, had they not, if you were on a different problem type or something that worked out specifically different, you do need to be careful. But here, since you're multiplying sine by cosine, they should have the same hypotenuse, so it should just cancel. Okay, for cosine, we're going to do cosine squared, so negative 7 over root 52 squared minus sine squared, root 3 over root 52 squared. Negative 7 squared is positive 49. Root 52 squared is just 52. Minus root 3 squared is just 3. Root 52, oopsies, becomes just regular 52 when you square it. I'm going to subtract those, so this is 46 over 52, but I will simplify in a second. I was getting ahead of myself. Both of those are even, so cutting them in half gives me 23 over 26, and that is the cosine of whatever angle is twice as big as the one they gave me originally. It is good to notice that these denominators should still match because the hypotenuses of this bigger angle should still be the same, and so that's important to note. For tangent, again, since I already did the hard work of finding sine and cosine, I'm just going to use my quotient. So I'm going to do negative 7 root 3 over 26 all over 23 over 26. I'm going to multiply by 26 over 26. And I get negative 7 root 3 over 23. That does not simplify, so that is my final answer. Again, one more example just for making sure you have plenty. Feel free to give this a try or just go ahead and listen. So sometimes we struggle with this Pythagorean theorem, so in case this is something you didn't like from earlier in the year, I'll make sure to actually talk about it a little bit here. When I'm solving this, you're doing 3 root 2 squared plus that missing side equals 5 squared. When you square this first part, do make sure you square both parts. So 3 squared is 9, root 2 squared is 2, so it's 9 times 2 or 18. And then you're going to go ahead and subtract and solve, and you get x equals the square root of 7, because you do 25 minus 18. I'm going to erase that so I have more room. But then let's go ahead and set this up. They already gave me sine, so I'll just fill that in. This is in quadrant 3, so cosine will also be negative, and it will be negative root 7 over 5. And then tangent is also negative, or sorry, tangent here is positive One thing to note, if you each time are finding sine and cosine and then using your quotient as we have been doing, you technically don't have to find tangent. I'm labeling it here in case you choose to use your other identity. Either way is fine. If you're using your quotient, this is optional. For sine of 2 theta, we're doing 2 times negative 3 root 2 over 5 times negative square root of 7 over 5. When I do this multiplication on the denominator, I get 25. 2 times negative 3 times negative 1 is positive 6. Root 14 because of the 2 times 7. None of that simplifies, and so that is my final answer. For cosine of 2 theta, cosine squared, so negative root 7 over 5 squared minus sine squared, negative 3 root 2 over 5 squared, gives me 7 over 25, because those negatives cancel, minus that 3 root 2, like we did in the Pythagorean theorem, is 18 over 25, which gives me negative 11 over 25. And then last but not least, for tangent. Again, since I already found sine and cosine, I might as well let that work for me. So 6 root 14 over 25, all over negative 11 over 25. You multiply by that LCD, which really just cancels them out, and you have negative 6 root 14 over 11. That negative can go wherever it wants, so you can put it in the front, put it on top, put it on bottom, whatever makes you happiest.